In this video, we're going to take a look at an oscillating spring system, but we're only going to be focusing on a portion of its movement to find the x value, the amount of stretch that the spring is going to have once it is dropped from a specific position. So if we take a look at our starting scenario here, we have a K value of the spring of 200 newtons per meter, and this 2 kilogram block is pushed up and compressed 0.1 meters. And then once it's released, we're going to look for how long it stretches from its equilibrium position. So after it compresses, it's obviously going to drop downward, and then it's going to hit some maximum position over here. When it does that, it's basically reaching its baseline height, so we'll basically call that height of 0. All right, now from there, we want to analyze all the different types of energies in the beginning and the end. So if we're using the conservation of energy, we can basically say all the initial energies equal all the final energies if there is no work being done, no heat or sound being created. So we have some initial energy in the beginning. We have the spring is pushed upwards, so we're compressing a spring, so we do have some elastic potential energy, and it is above our baseline height of 0, so we also have some gravitational potential energy. On the bottom end, it's going to move, it's going to have some kinetic energy, but it's going to stretch to its maximum position and momentarily come to rest, and then it's not going to have any gravitational potential energy because we call that height 0, and it's not going to have any kinetic because, like I said, it's momentarily coming to rest. So because it is stretching, it will, again, have some elastic potential energy. We'll call that the final, and then we'll call this the initial. So what we can do is we can go ahead and expand these out into their formulas, but there are definitely some tricky parts to it that we want to pay attention to. So we have the elastic potential energy in the beginning. We can call that 1/2 K x squared. And then we have our gravitational potential energy in the beginning. That one we can call it mg. And we don't know the h value. So what we know is this. We know that it has an equilibrium position somewhere around here, and it's pushed 0.1 upwards from that position, and then it's going to drop down and it's going to stretch to its maximum value. So let's go ahead and call this amount of stretch our x2, which is our final thing that we want to look for. So we can call our height x2 plus 0.1 because this compression over here is going to push it upwards an additional 0.1, and that's going to be all of our initial energies. And then after that, we're going to set that equal to our final. Our final is just the final elastic potential energy, 1/2, same K value of 200, and we don't know this x2. That's what we're looking for. So if I'm taking a look at all my numbers here, I do only have one unknown variable. So let's go ahead and rearrange this a bit and condense some of these numbers and see what we get for our x value. So what I did is took the product of these three numbers and it came out to 1 joule exactly. I took the 2 times 9.8 and distributed that 19.6 to the x2 and then the 0.1, which gave you the 19.6 x2 plus and the 1.96 joules equals 1/2 times 200, which is 100, the coefficient of the x2 squared. Then I took all of these numbers on the left and I scooted them over to the right. So the 100 x2 squared stayed the same, but then these Rest of the values became minus because I subtracted them from both sides. So the 19.6 is just the minus 19.6 x2. The 1 and the 1.96 combined for 2.96. So when subtracted from the other side became minus 2.96. So then you could either use the Pythagorean theorem or go ahead and graph this and find the intersection points of where the graph hits the x-axis. And then you would find a positive value of 0.296 meters as your final answer. So when solving a problem like this, you want to make sure you draw a good diagram so that you can recognize where your lowest heights are, where your equilibrium position is, and where your stretch and compressions are, so that as you're setting up your conservation of energy type formula, you're able to properly label values as they are. Such as this tricky part over here, like the x2 plus 0.1. I would say that was one of the key components in being able to solve this effectively. So I hope that was helpful to you. Thank you for watching and listening.